Is begin with a beaker of just regular water. I'm going to put some phenolphthalein in the water, and you see the water begin to change colors. Changes colors because water is basic. You remember this from the first day of school, where I put the phenolphthalein in the water and it turned pink because water has base in it. Phenolphthalein is pink in the presence of a base. I'd rather it not be pink right now, so I'm going to put this in. What do you think I might have put in? The opposite of a base?
An acid.
An acid. Which lowered the pH again. How do we do that on the first day of school?
We blew.
Or blew into it. All right. Okay. I'm adding a couple of pieces of magnesium to the water. We're going to see over a period of time if anything happens to the magnesium in the water. We're just going to let it sit there while I do the rest of these demos. Okay. In this bottle I have some calcium metal. Calcium is what element on the periodic table?
20.
Okay, element 20. It's a 4s2 configuration. I'm putting the calcium in, and you notice that we're getting some bubbles forming.
Frozen back.
I'm lighting a little fire here on top, but watch what happens to the bubbles.
Oh, sweet.
Boom! The bubbles are a flammable gas. Okay. Calcium plus water turns into calcium hydroxide. What do you think the gas was?
No.
It's hydrogen. If it had been, because it was a flammable gas, we know that hydrogen was produced. So if hydrogen was produced, it should burn, which it did. Calcium hydroxide is produced. That would be a base. It's the first time you've seen a base formula probably in this class, but anything with an OH at the end is a base. If it's a base, then what should happen when I put the phenolphthalein in?
Pink.
All right, so we have a base that was produced. All right. The next metal that we're going to use is a piece of lithium metal. Lithium is actually stored in oil
Why?
in order to keep it from reacting with the environment. It's soft enough that I can actually cut it with a scapula, but it's a little bit difficult.
This isn't gonna blow up like it did in Mr. Voss's class, will it?
Hope not.
Huh?
That was so tight.
Oh god, that was tight.
But I've got my goggles on just in
It's
case. This is what the inside of the lithium looks like. And you can see that it's pretty shiny in there, like a metal should be. But it's a very, very malleable metal. So malleable you can just cut it. What's malleable mean?
Cuttable, spreadable. Easy to spread. Is that one or?
Or would you say that's more or less reactive than the calcium was?
A little less.
Similar, isn't it?
Yeah.
The bubbles, once again, burn.
Oh, this stuff is so lit.
It looks to me like the bubbles are coming off maybe a little faster.
Yeah.
Would you agree?
Yeah.
So we're seeing maybe an increase in activity. Back on now. So a similar reaction happened. Would you agree that the same gas came off? So the reaction is lithium plus water. It's lithium hydroxide plus hydrogen. And this time, since lithium only loses how many valence electrons? How many does it have? 1. So I only have one atom of lithium combined with one hydroxide. The hydroxide OH each accepts 1 electron. So I can only have a 1-to-1 ratio instead of a 1-to-2 ratio. So I had to balance the equation by using coefficients. Now if lithium hydroxide was produced, what should we see?
Pink.
You can see that it was making the pink. All right. Okay, sodium. The inside of the sodium is shiny like the lithium was. You might want to scoot back just a little bit. Just in case. Or it says more or less active. Now then, sodium is more active than lithium, and lithium was more active than calcium, right?
So, what trend does that follow?
So that's the we're looking at activity of metals here. I've got one more metal we'll try here in a second. So let's see. We'll let that burn out before I get into the potassium.
Wait, I know.
Potassium.
So really,
I actually have some more sodium. You want to see another piece? Well, since I got it here.
But it's just
yeah.
So sodium is more reactive.
Sodium seemed to be more reactive than lithium. It produced enough heat to keep or enough gas fast enough that it just kept burning.
But what do you put the big side? A really big piece.
I want to find out. That's about as big as I want to go.
Oh.
That may explode on us, so don't get too close. Cameron, lean back.
Oh.
I want to flood.
Sometimes that happens.
Nice.
I was like,
I want to swallow.
right, now. Pop that up. Pop that up. You've got the sodium. It's the same reaction. We've got the sodium hydroxide plus the hydrogen balanced the same way. Which one? We saw more energy come out of the second one, but that's a little bit misleading. Where do you think the energy is coming from? What was that explosion?
It's gas.
It was combustion of what? All of this fire comes from this. That's a reaction. So what happened is some hydrogen accumulated in the sodium. It was producing it pretty fast. It's covered with oil anyways. You get a little bubble of hydrogen formed and all the hydrogen blew up at once. So the explosion we saw was a hydrogen explosion. It wasn't a sodium explosion. The sodium is just creating the hydrogen very quickly because it reacts with the water fast. Right? So the hydrogen is created fast, so therefore there's enough of it to sustain a fast burn of the hydrogen. And what is an explosion? It's just a fast burn, fast combustion reaction, right?
Oh yeah.
Very pink again, so we know sodium hydroxide was indeed produced. All right, let me dump this. Is that we've just looked at? What do you think potassium is going to do? more or less active.
My ribbon's not wet. Stick a mushroom cloud like
Potassium also is a soft metal, and it's the softest of the four that I've been working with. It doesn't take much effort, just cut it. Notice how shiny it is on the inside?
Very cute.
So we
What do
just
they use
cut-
for like tooth fillings?
Not this. It looks like that. It's what they use for tooth filling is an amalgam of a couple different elements.
You just gotta put them in, yeah, close your mouth. Just like your teeth blow out.
This would give hot food a new definition. Redefine hot food. All right, here's potassium.
Dang, didn't even have to light it.
That was intense.
I'll put a big
It's double it all.
Mr. Howe,
Yes.
I have a question. So you know we have like potassium, calcium inside some of our food and it's like some of the meat? How,
Just like,
So what about that? They say bananas have a lot of potassium in them. Do they really have potassium in them? They could say that if they didn't have potassium in them, but what are they really talking about?
Well, I mean, again, it's like these are like real elements pretty much, but in like a banana is in a compound, so the reactive properties aren't the same.
What actually happens they're in a compound, and also they're separate. You have potassium ions, they have some other negative ions, and they're not necessarily joined in a banana. So in food, when we talk about sodium and potassium and so on, we're talking about sodium ions, potassium ions, calcium ions, not the elements themselves. Because the elements themselves do this when you put them in water. And you have not noticed a banana blowing up in your mouth. Okay. So what this demonstration is supposed to show you is that as you move in this direction, activity increases. All three of these are more active than calcium. And then what's the other trend? As you go down, they increase. At the beginning, I put some magnesium in my little beaker. And yet, I don't know if you've noticed it or not, but nothing's really happened with this magnesium. Except if you look down on it, can you get that on film? There's actually just a little bit of pink that's forming around the magnesium ribbons. So what's that mean? The magnesium is slowly doing?
slowly becoming paste.
It's slowly reacting with the water in the same way that all these other metals did. It's just a very slow reaction because it's not as chemically active. So would that make sense based on the trend that we're establishing here? So we've learned that as you move this way, activity increases, and as you move down, activity increases. All right? All right. So anyway, activity increases, you go down. Now, why might that be? Why might that be? Why would activity increase as you go down? What happens to ionization energy as you go down?
Yeah, it decreases as you're going down.
So it gets very much easier to remove an electron. Would that be from big atoms or small atoms? It gets easier to remove electrons. What's that?
Yeah.
Big atoms or small atoms? As you go this way and as you go down, activity increased.
Big
So it
atom.
gets easier to remove electrons from big atoms. All right, is that consistent with our size trend? Really, if you understand the size trend, you understand it all. The bigger the atom, the easier it is to remove an electron. All right, are we all good? Okay, so that's the activity trend of metals. On Thursday, we'll do a lab with activities of non-metals and see if they match up or not.